Hello everyone. Today I'm going to be talking about how we added LLDB integration to our emulator. Before I begin, I would like to emphasize that even though the talk will be about emulators, I'm hoping that a lot of these techniques will be useful to a wider audience. First, I'm going to talk a little bit about the emulator itself, and then I'm going to focus on the integration aspect. So the emulator I'm going to talk about is called GEMU. You can sort of guess what it stands for. And it's like an in-house ARC64 emulator with a focus on accurate emulation and first-class debugging support. I expect a lot of you will be interested in like how does it compare to other emulators. So I prepared a short slide like this. As you can see, like it lacks a lot of features that GEMU, for example, has, but it is able to emulate a single architecture very accurately and correctly, and it also supports a lot of debugging features. So in the rest of my talk, I would like to focus on the blue rectangle over there. So one of the features that is unique to our emulator is that it consists of two processes. So the first one we call the performer, and this is what represents the emulated process to the rest of the guest operating system. And then we also have another process which we call the compiler, and this is what really does a lot of the heavy lifting that's required for performing emulation. The advantages of this design are like twofold. For one, by moving a lot of the complexity outside of the first process, we lower the footprint of the emulator and enable more accurate emulation. The second advantage is that it makes debugging a lot easier because it allows us to use ptrace from the other process to debug the first one, and to maintain an active communication with LLDB even while the guest threads are busy doing their work. Another feature that's very important for accurate debugging support is signal handling. And this is because a lot of the things that the debugger, that LLDB will do to you are very similar to what an application can do to itself via a signal handler. So if you can emulate an application modifying its own state via a signal handler, you have made a lot of progress towards debugging support. And to make this work, the most important part is being able to take signals at guest instruction boundaries. So even if the host signals arrive at in the middle of a guest instruction, we need to have enough metadata to be able to create the illusion that it either arrived before the instruction or afterwards. Once we have that, the rest of the emulator operates relatively simply. The debug step waits for for something to happen, say a breakpoint to get hit or watch points or whatever. Then it checks whether all threads are stopped. If not, it sends a signal to wake them up. And once all threads are stopped, it lets LLDB know and does whatever it's asked of. Now moving on to the integration part. Once we've implemented all of the things so far, we are already able to emulate debug emulated applications with LLDB, but the process is not very user-friendly. Like it's required to start the emulator in one terminal, switch to another, start LLDB there, get the two of them to talk to each other. And this is something we wanted to improve. And while a simple solution might be to just create a script that automates this process. The disadvantage of that is that user needs to learn a new command, and whenever the user needs to restart the debug application, he needs to exit LLDB and thereby lose all of the state of his debug session. So the way we solve this problem is by creating a custom LLDB platform plugin, which is just like LLDB's abstraction for the machine or the environment that runs the debug application. And this allows us to customize the way that you start the debugging, the way you attach, the way you retrieve files, and so on. The interface itself is very big, but unless you're adding support for a brand new platform, you usually don't need to implement a lot of these things. For our use case, it was enough to implement just a handful of methods. The simplest one is basically this. It just tells LLDB what kind of binaries are we interested in. The second method is debug process and tells LLDB how to start debugging. If you look closely, you will see that this very much resembles what the manual steps I had a couple of slides back. But because this is all done now within LLDB, the process is completely transparent to the user, and the user can just run the process using any of the standard LLDB commands. Attaching is slightly more complicated because we need to establish communication with an already running emulator. And the way we've done that is by having the emulator listen on Unix domain sockets and provide information to LLDB. So for each emulated process, we have two sockets. One of them is the process info socket, which is essentially the emulated version of the proc file system on Linux. And it provides some basic information like the name of the process and so on. And the second socket is used for attaching. When LLDB wants to attach, it connects to that socket, and the emulator knows that this is a request to attach, and it should act accordingly. Finally, what we wanted to do is to make our platform the default for LLDB, so that whenever the user opens up an AArch64 application, it will automatically begin debugging with our emulator. And this is something that LLDB doesn't support very well right now, but it is possible to do it by a slightly hacky solution and using the LLDB init file. So a sequence of commands like this will cause LLDB to prefer our platform. And yeah, that's it. And that's all it takes to to make this work out of the box. If you have any questions, feel free to reach out to me after the session. Thank you.